They said something, there's gonna be new. Yeah, stuff like loose end. I'm not a big loose end. I know. Yeah, exactly. Tonight, it's the end of the night. All right, well, if he happens to show up. I don't care what happens to the papers. Then I'm done with my responsibility. You know what I like to do? Last time I gave. I got you. I'm nice to see what you're doing with some of the shots. Like my favorite stuff. Yeah, I left when you told me. I said. Yeah. I still want this album. I already. How do you do? Yeah, I thought even them here. Whatever. The familiarity. Yeah, no problem. I like everybody. Jeremy, like today I got the club. You don't have. It just started to like me. Doing here with they put me Thursday.
Yeah, the nights seem to be busy here.
Yeah. That was good tips for sure. As an example, they opened up a new window. Okay, welcome everyone. This is the December meeting of the DVAA. I'm Tom Nolasco, the vice president. And we'll start off tonight with this nova in M31. Now, it's not a supernova. A supernova would be as bright as, that probably, is that's M32, I think, and that's one. But anyway, but Gary just so happens, he was up at Cherry Springs and wasn't going to have multiple clear nights. He had one clear night. So just out of serendipity, he said, I'm going to shoot M31. It's a good night for it. And he shoots it. And lo and behold, though, 3 days earlier, on the 17th, a nova was seen in M31. And Gary zoomed in here. He kept zooming in and zooming in, zooming in. And there it is. And it's about 14th magnitude, I think. But in the picture here, it looks a little bluish. And this is what, there's been a lot of talk back and forth. Why is it blue and red and stuff? And this is what the AI comes up with, which is always right. You know that, right? And but it says, and now we think it would be the initial phase 2, where it's rushing out because things blue shift, I would think, So I don't know if this is true, but basically all the scattered dust and everything gives it a blue look for a short period. It is a red nova. It's the merger of 2 stars. So anyway, now the curious thing is here, you got a 78-year-old amateur astronomer in Japan, I'm gonna try to say this, Koichi Itagaki. This is the way it phonetically looks on Google anyway. And so he's the one who discovered this. And look how kind of buried it is. So it's like, this guy is real. How does this guy do this? Well, it's Koichi. He's not your average amateur. He has 12 monitors here. This is one of his. This is his main observatory area, but he has 2 others in other parts of Japan. And basically, it's clear every night at least one of those. So he really has this guy's no slouch. He discovered a comet in 2009, at least 3 asteroids, close to 200 supernovae, including that real bright one in M101 just 2 years ago, that one that went off. He was the guy who discovered that. So the way he does this is he basically sets these scopes up. He has 7 scopes, sets them up, and he basically runs through 1,000 galaxies, and he shoots 15-second exposure, 2 of those, just goes bang, bang, real quick, goes to the next object, bang, bang. And so he shoots 2 so he can compare in case there's something in there, he can go back with the second exposure and make sure he has it. And the same thing shows up, but this guy is a serious amateur astronomer. This is his largest scope. I think it's a 24, I want to say. Anyway, I thought that was curious. I had to look this up. I'm thinking, who is this guy? Oh, last month we talked about active region, I think it was 4272, and we said it has a high potential for an aurora. And sure enough, there was an aurora just, I think, 4 days after our meeting. And can you turn the light down a little bit, maybe, Brian, just a hair? Does it maybe show up a little better? Anyway, this is from Moorestown, New Jersey, and then Laura's in Collegeville area. Ken is down in Delaware. Even in Delaware, you can see that nice green and the red. Sandy's out in Lebanon, got some nice shots there. And this is me in the Hatboro area, but it was a little surprise. It was kind of nice. We were kind of we thought we might get one, but then we did. Okay, well, I was wondering if this next huge spot is the same one that's coming around now. Is that AR 4272? Because that was previously known from some other AR number. It already survived one whole revolution. Now this one's coming up, but this one's in the southern hemisphere, and AR 4272 was up here. But this may be part of a remnant of it. But this is the big guy. This is a whole new region that we didn't see before. But it's pretty active. Now it's not as convoluted as that 4272, but it's a little more traditional. But still has been flaring a bit. So keep an eye on this. There's a potential for more auroras coming up. So we'll have to wait and see.
Easily visible naked eye.
Oh yeah, it's an easy visible naked eye object. You want to have your eclipse glasses or something, or if you have solar filters on your telescope, it's a great view in a telescope if you have a white light filter on it. Really nice. A lot of detail. Okay, Saturn got real narrow, but it did not get, this was the curious thing, how easy would it be to see visually, even though it's down to less than 4/10 of a degree? And the answer is it was very easy still to see. I looked at it that night, the narrowest, and it was super thin, but it was a crisp line. It was just a line going through it, and it was real easy. I picked it up real easy. So this is a picture from that night, along with a few of its moons. And now it's starting to widen. So next year, we already do our star parties next year at Valley Forge in October or so, and when it's high enough in the sky.
All right, thanks, Wayne. So now it's my pleasure to present this evening's invited speaker who's going to be joining us via Zoom. So our speaker, you can see him up there right now, is Professor Michael Seeds. He's been a professor of physics and astronomy at Franklin and Marshall College since 1970. I don't know if I want to give away your age like that. So he's developed several courses over there, including archaeoastronomy and changing concepts of the universe. And he was the winner of the Lindback Award at Franklin and Marshall, which is a very prestigious teaching award. Michael is also the author of a number of books, including Horizons Exploring the Universe, Astronomy, the Solar System and Beyond, and Perspectives of Astronomy. He was also a senior consultant in the creation of the 26-episode telecourse accompanying the book Horizons Exploring the Universe. Actually, Don McCallernan would like to come up and a few words, as he's known Michael for quite a while.
All right, Mike, I hope we're going to be still friends after this. I knew Mike for over 20 years, and he's very knowledgeable on astronomy. But you know what Mike's true love is? Micromounting. What's micromounting? In the world of rocks, minerals, and crystals, the smaller they get, the more perfect they get. And under only a 10x microscope that Mike has a few of them, they look like Smithsonian samples, the rocks and minerals. And Mike has thousands of them. Right, Mike?
Yep.
We've traded micromounts. It's another type of hobby. So I have a feeling that Mike's topic with astronomy might overlap with micromounting. You might get a little sense of that tonight. So anyway, good luck, Mike.
Thank you.
All right, thanks, Don. So at this point, I'm going to turn the floor over to Mike, and he's going to present his talk. It's called How the Stars Made Dinosaurs and Us.
There we are. Well, thank you all very much for inviting me to your club meeting. It sounds like you have a very active and exciting club meeting. When I was in grade school and high school, I belonged to an astronomy club, and we met in members' living rooms. So my club was much smaller than yours. And thank you for inviting me to speak, because I like to talk about astronomy. And my favorite lesson from my students over the years was about the origin of the elements, because it's really a very personal lesson. And so I titled the talk Stardust, and this is the Stardust Casino in Las Vegas, which I thought was pretty. They blew it up with dynamite in 2006. Did that on purpose, by the way. The first few slides are slides that I use when I talk to a public group, not astronomers. And I have to remind them of certain things, or maybe tell them things they never knew. So I tell them this is the Earth, it's 8,000 miles in diameter, which is very, very small, and we share it with roughly 8 billion crazy people. And we can't leave, not yet. And this is the sun. It's just a star, just a humdrum star, not peculiar anyway, except that we live near it. And I remind them that there are other planets in the solar system, most of them larger than the Earth, and that they go around the sun. And I remind them that this diagram should be illegal. It is simply stupidly out of scale. And you've seen this diagram, and I point out that if this was our galaxy, we would be over there. And that a galaxy like this contains 300 billion stars. I've heard people say 400 billion or 200 billion. I figure once you pass a billion, it really doesn't matter anymore. So I'll say more or less. Astronomers say more or less a lot. And this is the time exposure, 11.3 days long, of a so-called empty spot on the sky. It was the first one made with the Hubble telescope. And it contains thousands of galaxies. Almost every point of light you see here is a galaxy, except that thing right in the middle. That's a star, and that's a star, And there's another star in here somewhere. I'll leave you to find it. The stars have diffraction fringes. Extrapolating from this, you can estimate that there are approximately 2 trillion galaxies visible with existing telescopes, and that's a lot of galaxies. I have to explain to them that stars are born from gas and dust in space. Clouds of gas become gravitationally unstable and they contract and form dense clouds, which eventually fall together and form stars, a cluster of stars usually. And those stars live for a few million to a few billion years, and then they die. They run out of fuel, and they make some elements while they're shining, and they return those elements to the interstellar medium, and new stars form. It's surprising to some people that there are generations after generations of stars in the universe. And I have to remind them that the planets formed around the sun in a cloud of gas and dust that settled into a disk, the so-called solar nebula, and explain then that the planets formed in that nebula. Here's a planet that is formed over here, and here's a planet that is formed over here. And the sun is now becoming very bright and is beginning to blow the gas and dust away. And in just a little while, in this photograph, all the gas and dust will be gone, and the planets will be orbiting the sun as the solar system. And so we are here. This is how we got here. Now, that was the fastest astronomy course you have ever heard. And now we can start talking about the origin of the elements. And I always told my students that the most interesting images in astronomy are they're graphs. And this is a graph that is in absolutely every intro astronomy book. And it is almost impossible for college freshmen to understand. It shows the abundance of the elements according to their atomic number. And here's hydrogen, and there's helium, and this is the carbon, nitrogen, oxygen peak, and this is the iron peak. And it has an exponential scale. What in the world does that mean? It doesn't mean much to college freshmen. So I took this data and I put it into an Excel spreadsheet, and I asked Mr. Excel to plot a graph with a vertical axis that was linear. I can think in linear terms. I'm not good at exponential terms. This is the linear graph. There's hydrogen at the top. There's helium. And everything else is down here about 1 pixel high or less. The carbon, nitrogen, oxygen peak sticks up a couple pixels. The iron peak sticks up a pixel. Basically, the universe is made of hydrogen and helium, and everything else is a smudge of trace elements. And the carbon, nitrogen, and oxygen peak is the stuff that we're made out of. So we are right there, the carbon, nitrogen, oxygen peak. So I want to talk about how these elements got made. And I want to use this diagram. This is a periodic chart, and a couple astronomers colored it to show where the different elements came from, how they were made. And the key down here at the bottom shows what each color means. So dying low mass stars make elements, and those elements are shaded yellow. So we're going to use this. We'll come back to it every once in a while to see how far we've gotten. And we have to start with the Big Bang, which was very, very big, or maybe it was very, very, very big, or I don't know. I'm not a cosmologist, but I do know a little bit about the Big Bang because we know it occurred, we can see it. The 3-degree background radiation is actually light emitted by the hot clouds of the Big Bang. It's been traveling through space for 13.7 billion years, and the expansion of the universe has stretched the photons as they traveled, and by the time it gets to Earth, those photons are stretched into the far infrared short wavelength radio range, and that's the background radiation, the 3-degree background radiation. So we know there was a Big Bang. If anybody gives you a rough time about it, tell them we can see it with the infrared telescopes. The Big Bang was hot and dense, and nuclear fusion could occur in it for about 3.5 minutes. By that time, the expansion had lowered the density and cooled the gas, and nuclear fusion had to stop. The only thing that could happen was that hydrogen became helium, about 25%. But the Big Bang couldn't make anything else. It couldn't make any other elements. And this is why. To make the elements, it had to go really fast. It only had 3.5 minutes. It had to start with a proton, add a neutron to make deuterium, and go up to light helium, and then normal helium, that's balloon helium that you put in balloons at the grocery store. And then you can make, oops, there's a gap. There's a gap at 5 atomic mass units. There's no nucleus at atomic mass number 5. If you make one of those, it falls apart immediately. And so the process couldn't get over this missing step, except there's some sneaky ways it can get around that and make a little bit of lithium and then make a little bit of lithium-7. And then there's another missing step. Atomic mass 8 is totally unstable. You can't make it. You can't make it last long enough to get to the next step and make beryllium. So the Big Bang could convert hydrogen into helium, and it could do almost nothing else. If we're gonna understand how the elements were made, we can't ask the Big Bang to do it for us. Let's start with stars like the sun. We're familiar with the sun. The sun is powered by hydrogen being fused into helium in its core. That makes energy and balances the gravity pulling the sun together. As it grows older, the sun will eventually fuse that helium into carbon, a little bit of nitrogen, and a little bit of oxygen. But those newly made atoms are trapped inside the stars like this. How do they get out of the stars? That's a problem we have to solve. How do the atoms that stars make get out of the stars? Well, let's look at the sun. As the sun gets older, it expands and becomes a giant star, 10 to 100 times bigger than the present sun. So when that happens in a few billion years, the surface of the sun will extend out to about where you're sitting. It will encompass the Earth. It will probably absorb it. People argue about whether any part of the Earth will survive. I don't know. It doesn't really matter because the heat and violence of the sun will drive the atmosphere away, evaporate the oceans, and vaporize the crust of the Earth down hundreds of kilometers, maybe 1,000 kilometers. Maybe there'll be nothing left. It's going to be bad news for the Earth. These stars become so big, they lose mass from their surfaces. They are so big, the surface of the star is a long way from the center of the star, the center of mass. So gravity at the surface of these stars is very weak. If you could stand on the surface of one of these giant stars, not a good idea, but if you could, and you dropped a baseball, it would take 25 minutes to reach your toes. That's how weak gravity is at the surface of these stars. And consequently, the gas atoms are moving fast. It's hot stuff. The gas atoms begin to escape. And so the stars, these medium mass stars that become giants, blow their atmospheres into space. It's not an explosion. It's not violent. It's just a poof. It might even take 1,000 years or 10,000 years, or people argue about how long it might occur in stages. Poof, poof, poof. Might take a few attempts to get rid of that atmosphere and blow it away. And you know what happens? We get planetary nebulae. Here is a medium mass star that has blown its atmosphere into space. This is the spirograph nebula. And this is a little expanding cloud that has been poofed into space. The star itself collapses to form a white dwarf. So this is one way that stars can get the atoms that they have made back out into the interstellar medium. Oh, the sun will do this in a few billion years, but please don't worry about it. It's a few billion years. The diameter of this thing is just under 3 billion light years. Excuse me, oh dear, no. At 3 light years, it's not a big thing. You couldn't walk across it, but it's not a really big thing for astronomical objects. Here's another one. This is the Cat's Eye Nebula. Probably has a binary star going around it. And this is another one. These things all have their own appearance, then that probably means there's all kinds of interesting processes going on that we don't quite understand yet. Binary stars and different stages of blowing the gas away. But we don't need to worry about that because we now understand one of the ways that stars can return the atoms they make into the interstellar medium. And here's a composite that NASA made of a bunch of planetary nebulae. You've looked at some of these. And you can see that some of these look like they have occurred in stages, poof, poof, poof. And some of them are asymmetric and all kinds of, they're very interesting things to study. The physics that's going on there must be really complicated. So let's see how these stars made their atoms. The process that happens is called the S process, the slow process. The stars live for 8 or 10 billion years. That's plenty of time. And although there are lots of slow cooker processes going on in these stars, those processes don't produce a lot of energy. They don't affect the structure of the star. Helium fusion makes a lot of energy, and that's what makes the star expand and become a giant. But these slow cooker processes can make other elements, like lead and carbon. I am particularly fond of carbon since I'm made of it, and nitrogen and strontium and molybdenum and barium. I hope you're not familiar with barium. There's a medical test you don't want to think about that uses barium. It's a very good absorber of neutrons and cerium and other atoms. And those get poofed back out into space and they float around, and eventually a new star forms. Maybe it has planets, and some of these atoms get incorporated. And if we look at the diagram, here's dying low mass stars produce atoms, and those squares are shaded yellow. Look at this: carbon and nitrogen. Most of the carbon in the universe, most of the nitrogen is made by low mass sun-like stars. There's lead. We mentioned lead. What else? There's tungsten, yttrium. I'm not very worried about yttrium. Look at this. Medium mass stars, sun-like stars, can make lithium. It's kind of a side project, these slow cooker processes. So there's one of the ways that lithium gets made. The Big Bang couldn't make much lithium. Now let's talk about massive stars because they're much more interesting and they're much more violent. That's the way TV shows are. The better ones, the more interesting ones are more violent. So let's talk about massive stars. Massive stars are more than about 8 solar masses. And they become supergiant stars and swell up to be 100 to 1,000 times the diameter of the sun. The sun isn't going to do that because it's not massive enough. They get really, really big. And you're familiar with some supergiant stars, Betelgeuse and Rigel. A lot of the visible stars in the sky are supergiants. They are just so bright, it doesn't matter. These stars are so massive, they get so hot, They can fuse hydrogen into helium and helium into carbon and oxygen, and they can go on and fuse the carbon. Stars like the sun can't get hot enough to fuse carbon, but these massive stars can fuse carbon and make silicon and sulfur and neon and so forth. This is just the inside of the star, the tiny little thingy in the middle, the core of the star. They can make iron, and iron is bad news. Iron is the most stable nucleus. You can't start a nuclear reaction with iron and get any energy out. So the star can't make energy when it develops an iron core. And if the iron core, as the iron core gets bigger and bigger, the star can't support itself and it collapses. It just falls into itself. Gravity wins. Kaboom. No, excuse me, not kaboom. Just boom. It's a supernova. We're going to meet explosions that are more violent than supernova. This is a new photograph from the Webb telescope of a star that exploded about 1 day before this photo was taken. Somebody noticed it brightening in the sky. The very next night, they used the very large telescope to take this photograph, and it shows the shock wave blowing the star apart. This disk, the reddish disk around it, is gas that must have been exhaled sometime before, long before the supernova, because this stuff had time to settle into a disk. So here's a star that has just begun to explode. You're familiar with supernovae, and maybe you remember 1987A, which occurred in the southern hemisphere. It was visible to the naked eye if you could get your naked eye into the southern hemisphere. I wasn't rich enough to do that, and I was teaching classes, so I never got to see it. This is a massive star whose iron core collapsed, and it exploded as a type 2 supernova. And it leaves behind a neutron star, or if it's massive enough, more massive than about 45 solar masses, it can leave behind a black hole. Now, it seems like a star that makes an entire core out of iron would be a great place to make iron, except the iron is destroyed. It's converted into a dense soup of neutrons inside a neutron star, or it's swallowed into a black hole. We don't get much iron from a type 2 supernova. But the explosion blows the outer part of the star apart, and some of the atoms that were made during the evolution of the star get returned to the interstellar medium. And I know you're familiar with the Crab Nebula. It exploded in 1054, and it left behind a neutron star right in there in the middle. The diameter of the Crab Nebula is about 11 light years. Remember that a planetary nebula is only a couple light years in diameter, 3 light years. The volume of these things goes as the cube of the radius, the cube of the diameter. So 11 light years is much bigger than 3 light years. So these are really big things because it's a really violent explosion. And these explosions are so violent, they can make atoms through nuclear fusion during the explosion, while the star is blowing itself apart. They can make all of these elements. It's called the R process, which means the rapid process. It can make sodium. I'm really glad because I like salt on my French fries. It makes magnesium. It can make oxygen. I have to admit, I have an oxygen problem. I am addicted to oxygen, and I need it, and I appreciate it. And thank you very much, supernovae, for making oxygen for me. It makes aluminum and potassium and phosphorus, makes arsenic. Don mentioned that I collect rocks, and there are lots of little arsenate rocks that are very colorful. So I like arsenic, not on my French fries. And it makes selenium, and it makes copper. I am especially fond of copper because I like electronic devices, and copper is a very good conductor. And it makes silicon because and I like silicon because it makes rocks. So all of these elements and others get made in type 2 supernovae, and they're blown back out into interstellar space, and they get incorporated into new generations of stars. Look at this. The green squares show what is made in exploding massive stars. There's oxygen up there. There's fluorine. We used to use fluorine to keep ourselves cool in the summertime, but we don't do that anymore. We got smart. We don't do that. There's neon. There's aluminum. What else can we find? There's cobalt. There's iron. Right in the middle. Iron 20. Iron right in the middle. More than half of all the iron in the universe was made by type 2 supernova. Oh, excuse me. I got my colors mixed up, didn't I? I'm talking about the green stuff. Some of the iron, the green corner here, was made by type 2 supernovae. We're going to make that blue stuff later in a much more interesting way. And there's vanadium and titanium. Notice that these atoms that are made in type 2 supernovae are up at the top. They're not real massive atoms. You want to make massive atoms, you got to get even more nasty. And that's what we're going to do next. Let's talk about white dwarfs. I really like white dwarfs because the physics is really, really weird. They're about the size of the Earth. They're about the mass of the sun. They are extremely dense, and I know you've read that a teaspoonful would weigh 15 tons. They're made mostly of carbon. The carbon that was left in the center of those sun-like stars, when the star poofs its atmosphere into space, the rest of the star collapses to form a white dwarf. The carbon can't burn because it can't get hot enough. It's not massive enough. It could burn, but it's not massive enough. But there is a way to make that carbon burn, because 50% of all the stars in the sky are binary stars, and here is a white dwarf that is orbiting around another star, and this star has begun to evolve. It is expanding and is losing control of its atmosphere, and that atmosphere is flowing into a disk around the white dwarf, and that shiny little bright spot is where the incoming gas hits the disk. That's not a star, that's just the point where it collides. The gas goes into a disk surrounding the white dwarf, and it slowly settles onto the white dwarf, and the white dwarf gets more and more massive. And if the mass of the white dwarf exceeds 1.4 solar masses, that's the Chandrasekhar limit, then it can't support itself anymore, and it collapses, and the temperature and the density shoot up, and the carbon begins to fuse all at once. A white dwarf is a carbon bomb just waiting to go off. An atomic bomb detonates a ball of uranium. I'm not sure exactly how big that ball is. Maybe I'm not supposed to know. But I think it must be a little bit bigger than a softball. A softball size lump of uranium detonated produces an atomic bomb. This is an atomic bomb. A white dwarf is an atomic bomb, not uranium, it's carbon. And it's the size of the Earth and the mass of the sun. That is a very, very big atomic bomb. And when it collapses, the carbon fuses all at once. The star is destroyed. The white dwarf is totally destroyed. And you get a supernova, a really big supernova. Kaboom. I put this in just to remind you that these things are very, very bright. If only we had one in the northern hemisphere, we could go outside and see it with our naked eye. Here's one that went off in a galaxy, and that's the supernova. And for a short time, the supernova is brighter than all of the other stars in the galaxy. And this galaxy probably contains 300 billion stars. And for a short time, that supernova is brighter than the galaxy. I don't know what that short time is. I suspect it's a day or two. But when I talk to supernova people, the people who study supernovae, they can't really give me an answer I can understand. I'm a teacher. I write astronomy textbooks. I want to know how long the thing is brighter than the rest of the galaxy, but they don't think about that stuff. So these explosions are so violent, they can make atoms that other kinds of supernovae can't make. This is a type 1a supernova. The rapid process can make these elements more silicon. Oh, we need silicon to make rocks, and calcium. I keep my calcium in my bones, and vanadium, which is actually in your bones, and copper in my cell phone, and zinc, and nickel. I rather like nickel because the nickel that the supernova makes is nickel 56. And it is an unstable radioactive nucleus, and it decays with a half-life of about a week into cobalt 56, which decays over a period of about 2 months into iron 56. And iron 56 is good old iron. It's what we make automobiles out of, and bridges, and stuff like that. Much of the iron in the universe is produced by exploding white dwarfs. And now I can talk about the iron square here and get it right. I'm sorry I messed up before. The light blue shows the material that was made by type 1a supernovae. And most of the iron, just a little corner is made otherwise, most of the iron in the universe is made by type 1a supernovae. And look at some of the other stuff. More silicon, we need silicon. There's sulfur, a little bit of argon, vanadium and titanium and chromium. Oh, we need chromium for bumpers and stuff like that. So these type 1a supernovae are responsible for the iron in the universe. Now we can have some fun. Massive stars that explode as type 2 supernovae can leave behind neutron stars. And I want to remind you that 50% of all the stars in the sky are binary stars, two stars that orbit around each other. So it's reasonable that some pairs of stars are very massive stars, and when they evolve and die, they leave behind a pair of neutron stars. A neutron star is about 10 kilometers in diameter, and it contains roughly the mass of the sun. It is very, very dense. It is so dense that nothing can exist except neutrons. The physics inside neutron stars is practically unbelievable. So far as I'm concerned, it's unbelievable. These things have intense gravitational fields. If you could stand on the surface of one of them, you would be smushed into a layer 1 atom thick. Don't do that. In this case, the two neutron stars are in orbit around each other, and their gravitational fields are so strong that as they rotate, the gravitational fields propagate outward at the speed of light. This happens for all binary stars, but neutron stars have such intense gravitational fields, we can actually detect those gravitational waves. I say we, I mean the human race can do it. I can't do it. We have detected gravitational waves from black holes and from neutron stars. So we know the neutron stars exist, and the gravitational waves carry away orbital energy. As the pair of stars loses orbital energy, they get closer, and they get so close together, they rip each other apart. Now, in newspaper articles and things, I read that the neutron stars collide. I don't like that word collide. No, they're not colliding head on. They're orbiting around each other. They just get closer and closer together. And finally, tides rip them apart. About the time that they are close enough together to be ripped apart by tides, they're orbiting each other about 2,000 times a second. That's unbelievable. 10 kilometers across the mass of the sun, and they're winging around each other 2,000 times a second, and the tides are so strong they are ripped apart. This is a piece of NASA artwork, and it's beautifully done. I really like it. You can see this star coming apart. This neutron star is coming apart, but there's a mistake. There are tides on the outer parts of these stars too. So the outer part of this neutron star should be coming apart. The artist didn't show that. Maybe he didn't show it because then he would have to explain why there's tides on both sides of the star. You can figure out from the abundance of massive stars and their lifetimes about how many neutron stars there are in the galaxy, and you can figure out how many pairs there are, and you can figure out about how often this should happen. It should happen about once every million years in a galaxy of our size. That means that from the time of the Big Bang until the Earth formed, that's 9.2 billion years, in that interval, there were about 5 million of these merging neutron star pairs. That's a lot. And these things can make interesting atoms that can't be made in most other ways. And there's lots of them. They go off all the time. Once every million years doesn't sound like all the time, but 5 million times in the lifetime of the galaxy. And the nuclear reactions that can occur during these mergers are really interesting. Gold atoms can be made by merging neutron stars, and platinum and silver. Are you wearing gold, platinum, or silver? You're probably not wearing rhenium. You're not wearing thorium, I hope, or uranium or plutonium. And antimony, and some others. These atoms are represented in this diagram. I'm trying to find it. Where is it? Oh, there it is. It's the orange stuff. Merging neutron stars. And look here. There's gold. Almost all the gold in the Earth, in the universe, was made by merging neutron stars. And there's silver, and there's platinum. There's iridium. That's the dinosaur element, remember? There's iridium. And here's iodine. I'm always interested to see that almost all the iodine in the universe was made by merging neutron stars. And look down here, there's uranium. All of the uranium and plutonium and thorium in the universe was made by neutron stars, except the half-life of plutonium is only 24,000 years. So when a neutron star makes plutonium, it decays into other stuff very quickly. But uranium has a half-life of 4.6 billion years. It's still some of that around. You can dig it up on the Earth. And thorium, there are thorium elements on the Earth. Thorium half-life is 14 billion years. So we've now made almost all of the elements we need to get along. But there's one more way to make elements, and that's cosmic rays. So to tell you about cosmic rays, I need a slide, a photograph of an empty part of the sky. Couldn't find one. Nobody bothers to take those photographs. So I use this one. Ignore this thing in the foreground. It's just supposed to be a picture of empty space. And ignore the stars, because we're not talking about the stars now. We're talking about empty space. Empty space isn't empty. There are atoms floating around there because these pesky stars keep poofing atoms out and exploding as supernovae and blowing stuff out. So there's all kinds of atoms floating around out there. A lot of hydrogen and helium, but heavier atoms too. And when supernovae go off, they can blast atoms out at such high speeds, they're traveling nearly the speed of light. Some of those atoms are going very fast, and we call them cosmic rays. Some cosmic rays are gamma rays. We're not interested in them right now. We're interested in the high-speed atoms. They're mostly protons, the nucleus of a hydrogen atom. Some of them are alpha particles, which are the nucleus of a helium atom. So if a cosmic ray zips through this empty space and it hits another atom, say an iron atom that's floating there, it can break the iron atom. Here's a diagram. This atom is minding its own business. It's just floating through space, la-di-da-di-da-di-da. It's moving along. And here comes a proton at nearly the speed of light. It hits it, and it breaks the iron atom into two pieces. This looks like a helium nucleus to me, but never mind. This is some other atom now. It has had a piece broken off of it. This is called spallation. And spallation can make a few atoms that fill out our diagram. The spallation process, it's called cosmic ray fission in this diagram. I don't like fission. It's not really fission, it's spallation. That's the pink area. It can make beryllium and it can make boron. And look at this over here. Here's another way to make lithium. Nature has to work really, really hard to make lithium. Thank goodness it does, because we need those batteries. So there's beryllium and there's boron, and we need boron, of course, to get our clothes clean, but also to make glass and ceramics. It's used in electronics. It's a nuclear absorber, so it's good at absorbing neutrons, and it's used to make alloys. And oddly enough, beryllium is used for exactly the same kinds of things. So now we have made all of the atoms in our diagram. And so we are here. Except for the hydrogen, the Earth is made of atoms that were produced by the stars. Now, I want to take a couple minutes to give you some perspective, because knowledge does not become understanding until you have perspective. So to give you some perspective, I need to ask you to think about a dinosaur. And I'm going to suggest this dinosaur. It's in the Smithsonian. I saw it when I was a little boy. I've seen it many times since. You've probably seen it. And we need to give this dinosaur a name. And I would like to name it Spot. Spot the dinosaur. So we can talk about Spot. We know a lot about Spot. Spot weighed about 3 tons. How do I know that? I looked up the mass of a big elephant, 5 tons, and I figured Spot isn't nearly 5 tons. Spot must be more like 3 tons. That's probably too big. Maybe it should be 2 tons, but never mind. We're going to do a calculation, and it really doesn't matter if I make a mistake of merely a ton, more or less. You can do some arithmetic. That's about 2.7 million grams. I know you're science people, you're astronomy people, and so you recognize a number when we write it as 2.7 times 10 to the 6th. That doesn't bother you. Oh, if I talk to the public about this, I have to spend so much time explaining what that means. And we can look up the mass of the biosphere. How do I know that? I asked Alexa. Environmental scientists really want to know the total mass of the biosphere. That's an important number for them. And they have figured out that the mass of all the living matter on Earth is about 5 billion grams. 5 times 10 to the 18th. So, if we divide Spot's mass by the mass of the biosphere, we can figure out that Spot made up only 1 part in 1900 billion of the biosphere, which is about 5 times 10 to the minus 11%. Oh man. Even my checkbook earns more money than that. That is a tiny percent. Now let's talk about your thumb. Your thumb weighs about 20 grams. How do I know that? I bought a hot dog and I cut off a piece about the size of my thumb and I weighed it, 20 grams. The average atom weighs about 10 to the minus 26 grams. How do I know that? That's in every astronomer's head. And besides, you can ask Alexa. So your thumb, if we divide the mass of your thumb by the mass of an atom, we discover that your thumb contains 2 billion atoms, more or less. 2 times 10 to the 27 atoms in your thumb. If we assume that the biosphere has been well mixed since Spot died, I mean, Spot died. He was just walking along one day and he said, oh, 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 and he fell over and he died. And his body decayed and his atoms were returned to nature. They were returned to the biosphere. And there were storms that came by and floods and all kinds of things happened. That was 100 million years ago, so there was plenty of time for him to get mixed back into the biosphere. So I think he was probably mixed in pretty well. His spots are all over the earth. If that's true, then some of those atoms are in your thumb. In fact, 5 times 10 to the minus 11th percent of the atoms in your thumb were in the dinosaur that we call Spot. That amounts to 1 million billion atoms in your thumb right now were in the dinosaur that became Spot. And that's just for Spot. How many dinosaurs ever existed? Your thumb contains 1 million billion atoms, more or less, from every dinosaur that ever existed. Your thumb is probably beginning to feel pretty heavy right now, but you know your thumb isn't that big. It doesn't contain that many atoms. So that must mean that the atoms in your thumb have been inside more than one dinosaur. Dinosaurs died, their atoms got mixed up, new dinosaurs were born. Your atoms have been inside all kinds of things. They've been inside dinosaurs and whales and fish and germs and bacteria and mold and germs, a lot of germs, and bacteria. I mentioned bacteria, a lot of bacteria, all kinds of living things. And now you are using those atoms. You are made of used atoms, and they are very, very old. And rule number 1 is when you are done, you have to give your atoms back. Don't tell me about pharaohs who die in Egypt and have huge pyramids built over their graves. No. When the sun dies, it's going to drive off the atmosphere, evaporate the oceans, and vaporize the surface of the earth at least, and maybe destroy the earth completely. The pharaoh's atoms are going to be returned to the interstellar medium where they came from. That's just the way things work. Now I want to show you something that I found in a Target store. I was walking with my wife through a Target store some years ago, and I saw something that was so fantastic. I whipped my phone out and I started taking pictures of it. And my wife said, "Stop that, you're going to get arrested. That's little girl's underwear." Well, I couldn't stop. I couldn't. I had to snap a picture because I knew you would want to see this. Those are pajamas for little girls. And little girls are indeed made of stars. And so are you. We are all made of stardust. And that's the end. Thank you very much for listening. This was a lot of fun for me.
All right,
Yes.
all right. It's just not working. All right, is it working now?
Now.
All right. Let's switch to the other mic.
All right, thanks, Mike. That was a great talk. Does anyone have any questions?
Our minds are totally blown.
Is that a
Any
boom
questions?
or a kaboom of your boss?
Actually, one question I had, so you said the S process generated a lot of these very heavy elements, things like lead. Is there something else required? I mean, do low mass stars actually form lead out of helium and things like that? Or do they have to get sort of those medium heavy elements from the massive stars first and then kind of build on that?
Most of the processes are neutron addition, so it kind of hops up the stairway and makes the elements step by step. The slow processes are kind of side processes. They don't make a lot of energy, so they don't affect the star, but they do manage to make some elements even in sun-like stars. The more massive stars are really good at making elements.
I guess what I'm saying is, can you get all the way from, say, helium or carbon up to lead in one generation? Or do you have to go to a massive star first to make something else, and then that goes into a subsequent mass star?
No, I think you can get right up there. The slow process can do that and build up the atoms. But of course, the more massive stars can make all kinds of atoms, which are then returned to the interstellar medium and incorporated in other stars, which could be lower mass stars. The sun is now about 2% heavier elements, heavier than helium. But star formation and evolution and supernovae have gone on and made more elements. So the universe itself is now about 4% heavier than helium elements. So element formation has continued on, and we've been left behind because the Earth and Sun formed 4.7 billion years ago, and we haven't benefited from any of the atoms that the stars have made since then.
The question, is the concept of reincarnation fit into this scheme of exploration that you just described, which has been talked about recently in many cultures?
I'm sorry, did you say reincarnation?
Yes, but yeah, the idea of reincarnation and how that plays into this.
That is much more complicated than astrophysics. I'm not at all qualified to talk about that, so I don't know how I would fit all of that together. All I can tell you is the story of the elements and the stars.
Could I ask a question about the biomass of the Earth? Do you think that all the carbon in the Earth has been part of a biological process?
That's an interesting question. Just intuitively, I think there's a lot of buried carbon. Of course, some of that is buried in the form of coal and oil, which has been part of a biological process. But I think there's a lot of carbon much deeper than biological processes could reach. So there's probably carbon 1,000 kilometers deep in the Earth that has never been part of a biological process. That's just my intuitive guess.
Mike, McLaurin. I have
Yes.
a question. The gold was made from the neutron stars. Can you honestly say the analogy of everybody in this room tonight who's wearing a wedding band is wearing a fossil of a dead star?
I'd be willing to say that, yeah.
See that?
I'd like to see things like that. Some of you might be wearing wedding bands that contain a little bit of silver or a little bit of platinum. So yeah, those three elements are made in neutron stars, and they're used in jewelry.
to hold these things very delicately. So we know that you can manufacture up to uranium in stars, but are there really big hypothetical stars that can go even further, make the things that we typically think of as man-made, like technetium and things like that?
In the periodic diagram that we looked at, there were plenty of transuranic elements that are heavier than uranium, and those are made in stars. Yes, there isn't any kind of star that I know of that is more massive than maybe 100 solar masses. Maybe in the early universe, soon after the Big Bang, when there weren't any of these heavy elements, the stars could have been a few hundred solar masses. But they can't do that anymore because there's too many of these heavier elements that interfere with the flow of light out of the star. And so stars can't get as massive as they could back in the Big Bang days. So yeah, the supernovae, type 1A supernovae are the most violent, and they and type 2 supernovae, exploding white dwarfs and sun-like stars, manage to make all of the elements.
Other questions? Yes, it's like a great thought.
I hope I gave you something to think about. Astronomy does that.
Here, you want me to show you the crowd here?
You have a fantastic club. I really am impressed.
I think I disconnected the projector for a second there.
Thanks for a great talk, and hopefully we'll have you back at some point too.
That'd be fun. Thank you very much. Bye-bye.
Okay, that concludes our meeting for tonight. So you're free to hang out for a few minutes and just talk with each other, and make sure you have a safe drive home and be careful. And if you can make the business meeting tomorrow, come on out and see us at 1 o'clock. Good night.